Hey guys, welcome back to another video. My name is Melina, and today we're going to be going over a couple reactions with alcohols, ethers, and epoxides. So we're going to be going over protecting groups, oxidation of alcohols, how to make ethers, and how to open up epoxide rings. So the TBS Protecting Group. So what this does, it is that it ensures the Grignard attacks the carbonyl carbon, which is what we're used to, right? But in this case, the starting material also has an alcohol group as well as the carbonyl. Because the alcohol group is present, the Grignard can actually react with that and deprotonate the alcohol as opposed to just attacking the carbonyl carbon. So what the protecting group does is this TBS is the protecting group, and it attaches itself onto the alcohol group, which is, which is depicted right here. So now that this, the alcohol is now protected, right? What that means is it's capped. The protecting group acts as a cap, so it's no longer able to react with the Grignard. So now that it's capped, the Grignard can go through and attack the carbonyl carbon, and then it work up with the H2O, reprotonates it to make an alcohol, and then now you want to take the cap off, right? So TBAF is what takes off the protecting group, and then it brings you back to the original alcohol that was present here. And then this is the result of the Grignard reaction. Good. Okay. So now we have a couple of different ways to oxidize alcohols. The starting material here is a primary alcohol, and with a primary alcohol, you can do chromic acid oxidation, which is right here, and you result in a carboxylic acid, oxidizing all the way through. There are two other ways you can oxidize, which is the PCC oxidation or the Swern oxidation. And you can see that with both of them, you result in the aldehyde. So there's a little bit of selectivity when it comes to primary alcohols, depending on if you want the carboxylic acid or if you want just the aldehyde. So here's just a table I made, basically summing up everything I just said. With primary alcohols, there's all these reactions, but depending on what you want, there's selectivity in which reagents you should use. But when it comes to secondary alcohols, you're pretty much just going to get a ketone no matter what. And then tertiary alcohols, we cannot oxidize because that carbon already has all of its bonds filled up. There's no hydrogens present. So now we're going to go into different ways on how to make ethers. We have two different ways. This is the acid-catalyzed Etherification. And basically what happens is you have acid that's going to protonate the alcohol initially. And then another equivalent of the alcohol is going to come and attack this carbon, and the H2O is going to leave. That serves as a leaving group. And then now you're left with this, it's an ether, but it has an extra hydrogen. So another equivalent of the alcohol is going to come, just pretty much act as a base and deprotonate this hydrogen, so you get a neutral ether. And just remember that an ether is an oxygen with two R chains coming off, two alcohol chains. Next, we have the more common way of how to make an ether, which is the Williamson ether synthesis. And basically what you have is this NaH. The H is not an H+, it's an H-, and this serves basically as a base to deprotonate the hydrogen that's on the alcohol to form an O-. And this O- structure, has 3 pairs of lone pairs. One of those lone pairs is going to come and attack the alkyl halide you have here, Br leaves, leaving group, and you form this structure. Okay, next we're going to go into how to open up epoxide rings. We have two ways. The first is the anionic nucleophilic epoxide opening. And you start off with actually wait, let me go back. Something I forgot to mention about the Williamson ether synthesis is this is an SN2-like mechanism. So when this nucleophile attacks right here, this is a backside attack happening. So if there was stereochemistry shown, like wedges and dashes, this attack would result in an inversion of stereochemistry. Okay, moving forward. So like I said, we're going to open up some epoxide rings. This is the anionic nucleophilic epoxide opening. We're starting off with a Grignard, which is a really strong nucleophile. This is also SN2-like. So this is going to attack the less substituted side of the epoxide. So the Grignard attaches to this carbon. These get kicked off to make a lone pair. You make O-, and then H2O, the second part of the Grignard reaction, to basically just neutralize it, make the oxygen and alcohol. Last, we have the cationic nucleophilic epoxide opening. Here we don't have a strong nucleophile. We actually have a weak nucleophile. And because it's a weak nucleophile, it's not strong enough to open the epoxide on its own. So what we need is a little bit more help. So how we get the help is we have a little bit of the catalytic hydrogens present, H+. The oxygen on the epoxide is going to get protonated by that. Now it's a little bit more reactive and the weak nucleophile can attack. And because this is a weak nucleophile, it's going to attack the more substituted side of the epoxide. Remember, in the previous reaction, it's the less substituted side. But for this one, it's the more substituted side because this is more electrophilic and it holds a positive charge more stably. Like if you were to think of carbocations, remember, like more substituted is more stable. Tertiary is more stable than primary, per se. So the weak nucleophile is going to attack the more substituted side. These get kicked off to a lone pair, and you form this structure. Is this correct? 1, 2. Yeah. Okay. And then right here, basically what happens is something's going to come in just to deprotonate, take this off. It could be another equivalent of the MEOH. This as long as you take off this extra hydrogen and make a neutral structure. So that's all I have for you guys this week. Thank you guys again for watching and see you next time.